Hello everyone. Today we are going to simulate a half-wave controlled rectifier using thyristors on the LTSpice. Let's start creating the circuit diagram. So let's place an SCR. Then we will be in need of few resistors here and then a load resistor. There is a need for a diode as well. Then we will be needing a voltage source. Then let's connect these through the wires, and here you go. All right, so we also need a reference point, that is the ground symbol here. Okay, so this is the circuit diagram. Now let's select the component values as well as the components part numbers. First of all, let's choose a diode. We will be selecting a simplest diode, that is 1N4007. Then we need a minimum resistance, that is, let's suppose 1K, and there is another resistance that will be acting as a variable resistance, and we will vary it to change the firing angle of the thyristor. Then this is a load resistor. Let's set this value to 10 ohms with the name as RL. Then the source input is of type sine wave with offset 0, amplitude of, let's suppose, 24 volts with a frequency of 50, and all other things like delay angle, delay time, as well as the phase angle is 0. Okay, so we have selected the components with part numbers except this SCR. So for this SCR, we need a spice model, as there is no by default spice model available in the LTSpice library. So we will include it separately. So let me go to the spice model. So this is our spice model for the MCR 100,003, that is the SCR with a reverse voltage of 100 volts. Okay, so here let's go to the spice directive and then write .inc and paste the path of the file and place it here. Now let's open the thyristor. So here is the thyristor spice model, and you can see that this is the reverse voltage of 100 volts. Then the gate triggering current is 40 microamperes. Gate trigger voltage is 0.62 volts. Then there is a holding current, that is 0.5 milliamperes. And then we have the on time and off times and some other parameters. Okay, so this specific model has the name as MCR 100,003. So we'll copy this and paste it at the place of SCR name. So here we have selected the part numbers with the respective spice models. Now let's go to the configure analysis and set the simulation time to, let's suppose, 200 milliseconds, which is approximately 20 cycles for a frequency of 50 hertz. Then we will be setting a time step with a maximum value of, let's suppose, 10 microseconds, and place it here. And let's label this net as the thyristor voltage, and then label another net, that is this one, as the input voltage. So the voltage at this node with respect to this ground will be across this thyristor, a node to cathode terminal. And to find the output voltage, we will be taking a difference between the terminal voltage at this left hand side of this resistor and the right hand side. So that will be V in minus V thyristor, right? So let's start simulating the circuit. And first of all, let's see the thyristor voltage. So here is the thyristor voltage, which is approximately the complete negative half cycle. And now to view the actual output voltage, I will be taking the difference between V in and V thyristor. So this is my output, that is in blue color, and this is the thyristor voltage, that is in green color. Okay, so here you can see that for this specific variable resistance value of 1 kilo ohms, the complete half cycle is appearing at the output, and the complete negative half cycle is appearing at across the thyristor. Now let's change this value to, let's suppose, 100k, and run the simulation again. Now you can see that there is an introduction of a firing angle, and because of that firing angle, the a portion of the positive half cycle is also appearing at the across the thyristor, and the output voltage, that is in blue color, has a less RMS value or less average value as compared to the previous case. We can increase this value further to, let's suppose, 500 kilo ohms, and run the simulation again, and now you can see that the firing angle is further increased. So this is the firing angle starting from the zero crossing and then at up to this clipping point. Okay, so let's test this for another firing angle. So let me change this variable resistance to 1 mega ohms and see what we get at the output. Now you can see that approximately more than 60 degrees of firing angle is there, and that is why the output voltage is further reduced, and almost half of the positive half cycle is appearing across the thyristor. I can change this to, let's suppose, 1.1 mega ohms and see the output. Again, we can see that now this is even close to the 90 degrees firing angle. I can change it further to, let's suppose, 1.2 mega ohms and run the simulation again. And now you can see that this positive half cycle is also appearing across the thyristor, and the output voltage has become 0 volt. So it means this specific circuit is having the gate triggering part, such that the maximum firing angle achieved is 90 degrees. So this specific circuit is actually having the gate triggering part that is also being fed from the main input source, right? So there is no separate gate triggering circuit required for this specific configuration. And as the input voltage is a sine wave, that is why we have a diode here, because we can only supply a positive gate voltage and the positive gate current. So that is why we have a diode here. And out of these two resistors, this R1 is the minimum resistance that is required, because whenever this variable resistance will get 0, then all the voltage will be appearing across the gate of the thyristor and it may be damaged. So that is why we must need a minimum gate resistance, and then a variable resistance that will be used to vary the firing angle. So from this specific circuit, we can conclude that the maximum firing angle achieved is 90 degrees, up to 90 degrees, or it is less than 90 degrees, right? So in the next video, I'll be posting another configuration that will be also having the gate triggering part being fed from the main input source, but the firing angle range would be approximately up to 180 degrees, right? Okay, so in this specific circuit, so let me show you the gate triggering voltage, right? So I can see this gate voltage. So this is now the gate voltage. That means the gate will be triggering at this peak value, right? Now let me reduce this voltage to, let's suppose, reduce this resistance to, let's suppose, 500 kiloamps, and run the simulation again. Now you can see the maximum value of the gate spike is at a firing angle less than 90 degrees. So that is why at this specific voltage, I will be getting a firing angle less than 90 degrees, right? And now I can further reduce it to, let's suppose, 100K, and in this case, I will be seeing a less spike at the gate terminal, uh, a spike at a less firing angle as compared to the previous case. So in this case, I can see the output, and you can see that the firing angle is maybe less than even 45 degrees, right? So that's all about this half wave control rectifier, and in the next video I will be simulating a half wave rectifier with a firing angle range of up to 180 degrees. Thank you so much.